we're gonna start today's lecture, and like just to wake us up, we will start with a reasonably simple problem, but it is still interesting for one of the things it will show you in its solution. And the problem looks as follows. We have a very, very tall skyscraper. Okay, I will switch to a different color because this black did the usual trick of working when I was trying it on the board over there and then stopping working. So hopefully we'll see something in this picture. I'll switch to a different whiteboard marker afterwards. So we have, as I said, a very tall skyscraper. The floors are numbered from 0 on the bottom to n-1 on the top, and n can be up to 10 to the 18, as usual, so that it fits into a 64-bit signed integer. And we have in this building a very impractical elevator. The elevator starts at the bottom floor. It has a very useful button, return to the bottom floor, so that anybody can go down with the elevator. But for going up, there are only 3 buttons, and the buttons say +A, +B, and +C. And the values A, B, and C are specific constants up to the 10 to the 6. So one of the obvious things is that the elevator is only perfectly useful if one of these 3 numbers is a +1, because if there is a +1, you can use it to go up any number of floors you like, and if there isn't a +1, there is no way of using the elevator to reach floor 1. Any other button will bring you just higher up the building. So that's the boring part. Now comes the actual question we are asking in this problem. So as you can tell, depending on what A, B, and C you choose, some of the floors will be reachable by this elevator, some of them won't. And the question is, given A, B, C, and N, count the number of reachable floors within this building. And when you are asked this question, probably your mind is first, as a first attempt, what to do with the question is jumping to some discrete mathematics. So this is resembling some things you may have seen elsewhere. In particular, one very famous result of this type is the chicken McNugget problem. It's also known as by some other names, but chicken McNuggets are the usual story how it is presented. So when you go to McDonald's, you can purchase the nuggets, and they are sold at different package sizes. You can purchase 6 of them, or 9, or 20. And the question there is whether there is some threshold beyond which you can purchase any specific number of McNuggets. And it turns out to be the case that yes, there is. I think 43 or something like that is the boundary, and anything bigger than that can be assembled as a combination of some 20s, some 9s, and some 6s. So something similar will almost certainly be happening in our building as well. But there are all kinds of unpleasant things going on there, right? So even if there is some floor such that from there on everything is reachable, there can be some not random, but hard to describe noise going on in between on those floors that some of them are and some of them aren't reachable. And what's worse, it doesn't even have to be the case that all of the floors beyond certain point are reachable. Why? Well, common divisors, yes? So if both A, B, and C, all 3 of them, are divisible by the same value D, then clearly all of the floors that you will ever be able to reach are just multiples of D. So there is definitely this extra step that you need to find a common divisor, factor it out, and then process it. And it starts to be unpleasantly complicated what to do with a problem like this. And yeah, we still have like some general ideas of how these values behave, but not really anything about how to do the counting in between on these floors that some of them are and some of them aren't reachable. And there is a lovely trick to solving this problem without resorting to any special cases, and just by letting a computer do some of the work. And the trick, and this is the reason why I really like this problem, is breaking symmetry. So the statement of the problem is perfectly symmetrical. There are 3 buttons, each equal to the other. Each of them is doing the exact same function, just with a different constant. But in order to solve the task, let's break the symmetry and let's say that this button is red and the other 2 buttons aren't red. So the red button is special. What happens now? So let's focus on the special button and separately, and the other two buttons separately as well. And one of the things that is clear about pressing these buttons is that the operation is commutative and also associative. So it doesn't matter in which order you press the buttons, it only matters which of the buttons was pressed how many times. So we can imagine that you are first pressing the ordinary buttons, and only then you will be pressing the special buttons. So what happens now, if you can use the buttons plus B and plus C to reach any floor in the building, you can then use the special button to reach each and every building, each and every floor of the building that is a multiple of A higher than that. And this already seems to indicate the proper idea. So as soon as low in the skyscraper as you are able to reach some remainder modulo A, then from that point on, all of the floors with that remainder will be reachable. Because from this floor you can do plus A as many times as you want. So this turns the original question about determining which floors are and which floors aren't reachable into a much easier one. For each remainder modulo A, and there's only 10 to the 6 of them, we are now interested in the lowest floor with such a remainder that is actually reachable with the other two buttons. If there is no such floor, then this entire remainder class is unreachable. And if there is such a floor, or if there are multiple such floors, we are only interested in the lowest one of them, because as soon as we know the lowest one, we know that everything above it is reachable, everything below it in this modulo class is not reachable. And how do we answer this question? Well, this is a very simple graph problem, right? So we have the vertices are the remainder classes, modulo A, so we have vertices labeled from 0 to A minus 1. And from each of them, if you are at the floor, you have two options. You can either do plus B, or you can do plus C, and it will bring you to a different floor, and in particular to a possibly different, possibly the same remainder class. So from each of so we can imagine a very simple graph where you have vertices from 0 to A minus 1, and from each of them you have an edge going plus B, and of course modulo A, and going plus C, and of course modulo A. And what I'm saying now is that in order to compute the information for each remainder class, what is the smallest actual number of the floor with this remainder that can be reached? These are simply the lengths of the shortest path. So you start at 0, you follow the edges of doing plus B or plus A, and for each of the remainder classes, you are looking for the actual shortest path that will get you there. So we will just build this graph in linear time, run Dijkstra and log n, and then you can compute the answer again in linear time. So by breaking the symmetry, by making one of the three buttons special, we can solve the task in very reasonable way in a few lines of code. So this is a lovely example problem of the technique breaking the symmetry. And this is something that doesn't come up that often in problems. It is quite rare, but therefore it is special to my heart. I like this problem really. Okay, does this make sense to everybody? Are we woken up? Great. Okay, so now let me show you one very simple problem, just very briefly without going into the details, and then I will explain why I'm showing this particular problem. The general type of problems I now want to mention is bin packing, and bin packing is the whole class of problems where we have objects of some sizes and we have bins of some other sizes, and we are trying to fit the objects into the bins as perfectly as possible, to use as few bins as possible, or to given a fixed number of bins to pack in as many objects as possible. And generally we know that many of these type of problems are NP-complete or NP-hard optimization problems. For instance, already the knapsack problem with a single large bin, many objects, and trying to optimize some value functions or just trying to optimize the fit into the bin. These are already NP-hard versions of the problem. And we also know that simple greedy strategies often perform quite poorly. So if you, for example, consider a situation where you have 3 bins that looks like this, all of the same size. And now we have a collection of items. One of the very easy strategies you can use to put the items into the bins is to take the items, sort them by size, and so on. And then just greedily fill the bins, starting, for example, from the smallest. Always you take the most empty bin and put the next item there, so you'll get something like this, and then maybe this one will fit, and then the next item will already be too big and it doesn't fit anywhere. So the greedy strategy for this particular greedy strategy for this particular bin packing problem often performs quite poorly. Okay, and who can see through the metaphor and what am I talking about at the moment? So the metaphor is the 3 bins you have there in this particular picture. This is your time during an actual ICPC round. You have 3 contestants. Each of the contestants has 5 hours. You are trying to fit in as many of the problems you are solving as possible to get as many balloons, as many points, as the good medal afterwards. And almost all of the teams in almost all of the instances of the ICPC are doing it using this particular greedy strategy. Pick always the easiest problem, the first available person, and have them solve the particular problem. What happens then? As we are getting closer and closer to the end of the contest, you are left with the harder problems. You are left with a lot of person time available, but you are not left with any single person with enough time available. And this is not even talking about the use of the computer yet. So the place where many of the ICPC contests are won or lost is usually the last hour of the contest. And the most important bit of contest strategy, at least in my eyes, is making sure you are utilizing the last hour of the contest properly. There are many other things in contest strategy we can talk about, and if I do have the opportunity, I can talk to you about them, but at this particular moment, I want to focus on this particular bit of the strategy because I think this is the most important one, and this is the one that makes a lot of a difference. So first of all, you need to make sure that your brain still functions during hour 5. This isn't for free. Like 5-hour competitions are a lot of strain. So this is something that, like even now, I mean, I'm terribly out of practice as a competitor, and if you set me now at a computer and let me have a 5-hour contest, I would probably be fine during the first 3 or maybe 4 hours, but I would definitely struggle during hour 5 simply because my body isn't currently trained to do this type of continuous focus, continuous performance at such a rate that it was when I was competing more regularly. So this is definitely something where just taking the practice contests helps. And this is also why practicing by actually solving all virtual contests makes more sense than just taking it one problem at a time, because you are practicing not just problem solving, but also this type of endurance. And it shouldn't, when I say endurance, it also shouldn't be just endurance. It shouldn't just be you actually pushing your body to be able to focus for 5 hours straight. This isn't really possible. But you need to realize also during these trainings, and you can also start practicing this today and tomorrow during the last 2 contests that I've set for you, is managing your body. So your body is a tool you are using to solve your problems, and you need to take care of it. So you need to try to take regular breaks to just breathe, to let your body relax. If you think back to like normal school education, we have classes, and between those classes we have breaks. Why is this the case, that there are these regular breaks? Well, because research has shown that people are not able to maintain continuous focus for a long time. It's much better to take those breaks, let the brain rest, and then a well-rested brain can focus better. So the final output, if you do this, if you take regular breaks, go to eat some refreshments, go to a bathroom and actually spend the time relaxing instead of trying to think about the problem, but now without the pen and paper, it will pay off. The integral of your performance will actually be bigger if you take these regular breaks and take care of like mental hygiene. And also, your brain needs energy to work, so don't spend the entire 5-hour contest without any drinks, without any food. Like quick sugars are essentially the same thing. It's the same thing as if you watch athletes perform, like for example the cyclists at the Tour de France. Every stage is multiple hours of performance. And it doesn't matter whether the performing organ of your body are the legs or the brain. It needs the energy, and it needs it in a form that it can quickly process. So eat sugary stuff during the contest if you can, if your health permits you to. And have your brain actually well fed and be armed to deal with the challenge. And when you are actually able to perform during hour 5 of the contest, now comes the question what to do with the contest strategy. And what paid off for us as a team when we are competing with some of my friends is we usually were trying to do kind of like briefings at regular point during the contest to just reassess what is our current state, what the contest itself looks like, and then what we should do in the next hour maybe of a contest. So maybe like aiming for 1 hour at a time. It was what we were trying to do, and we were doing it slightly less regularly than that, but it was still very useful. So the first such briefing happens after we have read through the problem statement, one person each problem, and possibly even solved the easiest problem of the contest. This isn't definitely a given. There can be, especially like in World Finals, it can be the case that you read the entire problem set and nobody finds anything that is like directly, I can pick this up, write the code and submit it. And in that case, well, you will just do the briefing at that particular moment in time. In other cases, you can have one person actually saying, oh, this is easy, I'm going to code this. And during the time, the others finish reading the rest of the problem set. And then you go through the problem set together. The important bit here is that difficulty of problems is subjective. There isn't an easy problem objectively and a hard problem objectively, or well, they are, but only to some extent. The single major thing that influences difficulty when you are at a team contest is your individual experiences. So one of you can be like an expert on graph algorithms, or one of you can easily have seen something similar to this particular competition problem that the others haven't. And for like intermediate teams, it still happened, in my experience, quite a lot, that only after the contest, somebody realized that, yeah, this other problem you were struggling with the whole time and that you said that you will do, and then you spent an hour and a half and 3 wrong answer attempts and debugging. I have seen this before, and I would have done it in half an hour easily because I know this problem. And this is because the lack of communication within the team. So very quickly in the contest, it pays off if each contestant on your team has an idea about all of the problems. Just very quickly, the person who actually read the statement can do a 30-second briefing about the problem. So this seems to be a graph theory problem about like connectivity multiple times between different places, something along those lines. And yeah, then based on this, more like all of you are more and better informed about the problems, that you can take more informed decisions. And at some point, when we are getting closer to the end of the contest, maybe an hour and a half before the end of the contest or at some point like this, it usually pays off to start thinking in terms of what is the actual number of problems we still expect to get solved, and how do we plan to do this? Who will be working on which of them? And you are trying to prevent exactly this type of a situation, that at 4 hours and 7 minutes in the contest, or 3:59 or something along those lines, you have submitted the last problem for which you had the actual idea how to solve it. And now you are left with a bunch of hard problems and the last hour of the contest. And 1 hour may not be enough to solve any of those problems completely, even if you are as a group working on it together. Some problems simply need you to spend like 3/4 of an hour working on paper, analyzing it, coming up with the details of the implementation, the corner cases and everything, and then you can sit down and spend half an hour implementing it. So it often pays off to start thinking about this way before the last hour of the contest, like what to do with the problems and whether there is something like, okay, the two of us will focus on finishing the problems we currently know how to solve, and you, the third person, who looks like, for you, this particular other problem looks promising that you don't know how to solve it, but it's your type of problem, and you think that if given enough time, you might be able. Possibly the best strategy now is already way before, an hour before the end of the contest, dedicate this one person to work on this particular hard problem and maybe get the +1. And +1 problem at a contest like the ICPC finals is an awful lot. +1 problem is usually at least the difference of a single medal or something like that. So yeah, so this is, I think, the picture to remember when you are solving a hard contest. This definitely applies much more to contests where you are going to run out of easy problems than it applies to contests where there are a speed race. If it is a contest where you can pick up any problem, look at it, and have a general idea of the solution, this strategy doesn't really matter that much, because you can just go. In this case, the greedy strategy is actually almost the optimal one, and the differences it produces are much, much smaller than it is in the case where there are problems that actually require a single person to spend way more than an hour on the problem before they can get it accepted. And of course, everything I'm talking about is made even more complicated by the fact that this is a game of not exact data. This is a game of estimates and probabilistic results. So we probably can get this problem accepted, but maybe we don't see some tricky corner case. We probably can finish this implementation, but it is really tricky, and it may be the case that I will be debugging it until the end of the contest, and so on. So the important advice is the meta advice. Take the time as a team to stop, breathe in, breathe out, look at the current contest situation, and re-evaluate what is currently going on and what seems to be the best strategy going forward. As soon as you start taking, if you are not doing this yet, as soon as you start asking yourself this question and having actually this discussion, you will see that it will improve the expected result of your team in the contest very quickly. And re-evaluating your situation, of course, doesn't involve only looking at your particular state of what you know about the problems. It also involves the scoreboard. So yeah, this is the obvious way that everybody of us is doing in the individual contests. Don't forget about it in the team contests as well. Look at the scoreboard. Scoreboard is giving you information. Don't forget that the scoreboard is giving you information only in one direction. Scoreboard can tell you that the problem is easy by seeing that many teams have solved this and we don't, so there may be something we are missing. This is useful information because it happened to me multiple times in a contest. Then in the attempt to read the problem statement quickly, I missed something or misread something or misunderstood something. And one of the signals you are getting from the scoreboard, if there is a problem everybody else is getting and you are not, is that, okay, it may not be the case that we are dumb. It may be the case that we are solving and not the correct problem, and that's why we cannot solve it. So if you see many teams getting it and for you it seems to be a very hard problem, it may be the case that you are just dumb in this case, or it's a problem everybody else knows and you for some reason don't. Those things happen and there is no shame in that, but it is much more likely that there is some other reason why you are not getting the solution. And the reason might very well be that you need to go back and reread that particular problem statement more slowly, more carefully. Dedicate one person to doing that if you see that this is happening. But yeah, back one conceptual step, I was saying that this scoreboard is only giving you information in one direction, that it's telling you that the problem is easy. It will not tell you that the problem is hard. If you see a scoreboard where nobody solved the problem, it doesn't mean that the problem is hard. Way too many teams, and even in the ICPC World Finals, way too many teams get directed what to do next to a very, very large extent just by the scoreboard. and they often let the scoreboard override their own like personal preferences and personal opinions about the problems. And this is also wrong. And there have actually been past World Finals where I remember a relatively easy problem, the problem that was estimated by both the judges and the analysts to be like somewhere in the middle of the pack, maybe even closer to the first half in the order of being solved, going completely unsolved during the entire contest. Nobody got around to it. And this was partially because the problem looked a bit scary to start it, so you needed to like maybe play around with it a little bit to get a feeling for what is going on, and afterwards it was reasonably easy to solve. But it wasn't obvious what to do with it, like when you read the statement. And this, with the combination of like nobody else tried it yet, led all of the teams to the strategy, let's just not look at the problem at all because nobody else did. And nobody ended solving the problem. And after the contest, like when people read the unofficial solution write-ups or talked to the writers of the contest, then they all realized, oh, this was something that was quite easy. We should have done this. Why had nobody done this in the entire contest? And this was an actual ICPC World Finals. So listen also to your own intuition about the problems. Don't listen to just what the scoreboard is telling you. And if you think you have a chance of solving a problem, go for it. In particular, the World Finals, because there are actual financial bonuses for being the first team to solve a problem. So if it is something in your wheelhouse, if it is something that looks like, oh, I like these type of problems, I may have fun with this one, even if the scoreboard is telling you that nobody attempted it, go for it. If the scoreboard is telling you that many teams have attempted it and nobody solved it, so if you see a bunch of wrong answers, this is a completely different story. This may be a reason to avoid such a problem. If you see this happening in a geometry problem, if you have anything else in the problem, said don't touch that one with a 10-foot pole. No. I mean, if everybody is getting wrong answers on corner cases in geometry, nobody is getting it right. That's the problem that's there as a safety valve. Like we don't want anybody to solve the entire problem set, so this is there. It's in theory solvable. We have we have exactly two reference solutions. So we have the reference solution of the problem author that was written during 2 weeks and debugged. And then we have a single tester who was actually able, with the presence of this solution and the test data, to debug their solution to match the other one. So this is enough to put that one. Okay, I may be slightly evil and exaggerating, and my very good friends who have set contest problems for the ICPC World Finals recently would probably slightly disagree with me. It is an exaggeration. It is not a serious exaggeration. It's similar to what actually goes on in reality. So if you see everybody getting wrong answer on a problem, it's completely different from the scenario when nobody is actually attempting the problem. So these are probably the main bits and pieces and ideas I currently have to contest strategy. When I think of something else, I will again make a break between explaining actual algorithms and talk to you about things like this. Yes?
What do you do if you realize you've made a mistake, for example, in assigning a problem to the wrong person, or
yes.
stuff like that? How do you backtrack out of that situation?
This is a very, very good question, and when we are competing at a high level, we are taking risks. So the answer to the question what to do with the mistake depends for me very much on what your goal is in the actual contest and what your ambitions are and how badly you want to reach those ambitions. So when it was our World Finals back in the day, it's now roughly 21 years already since I competed in the World Finals. The time is running so quickly. You blink once and you miss your entire life. Anyway, what was I saying? So when it's your World Finals, there is an opportunity that probably won't repeat itself so easily. So in order to get a really good result at the World Finals, you need to take risks and you need to hope that your risk will pay off and that your strategy will work. And essentially, you can afford like small mistakes. You can afford to have a wrong answer on a problem and then spend some time reading through it, debugging, fixing it. But as soon as multiple things start going wrong at the same time, and you have currently 3 problems that each of them has some written solution already by one of the members of your team, none of them got accepted, and now all 3 of you would like to debug, and you only have a single computer. These already things going so wrong that, yeah, your hope for the good result is already gone. And there is no good answer what to do in such a situation. You just need to like judge the current situation and make these estimates. Usually, like the level 1 answer to what to do when something has gone wrong is to prioritize efficient use of the single computer you have. This was slightly different now during the pandemic times, where there, for health reasons, there were like 3 computers per team, and it worked completely differently. But as we are going back to the standard ICPC rules and just a single computer, the computer definitely is a bottleneck, and using it efficiently is hard. And so for instance, it's really helpful if you can debug on paper, or if you have within the team, if you have the experience of one person being able to help other person to debug. And this is something that doesn't come again for free. This is something why it makes good sense to solve practice contests as a team, because these situations will come up and you will be forced to deal with them also during these practice sessions, and you will get used to how each of you as the team members operates, and what are your strengths and weaknesses. And I don't think there is any single universal answer what to do in such a situations, like for example when you said that you assigned a problem to a wrong person. In some teams can be reasonably balanced, that it can mean the difference between 30 and 45 minutes of solving the problem, and it could be the case that the best solution is just let it be and deal with it, that you will get the problem solved slightly slower, but now the other person is free to maybe do something else, and maybe you didn't lose that much time. In other situations, it may be the case that it's probably better still to have somebody else pick it up at that point, maybe spend a few minutes talking to each other about the problem. Like the person that already spent some time working on the problem didn't do nothing. They did some useful things, useful observations. If they share them, then the transition can be done much faster, and the other person will then spend much less time on the problem actually. And in order to make these calls close to optimally, you need to know each other in your team, and know your strengths, know your weaknesses, and know how to use each of you as a separate resource in the contest. One particular trick I can share that is related to this is this bit about helping the other person debug. You can try just doing like the standard type of rubber duck debugging. So you have somebody just sitting there, and you who are the one with the bug are explaining to them what you are doing, with the hope that at some point during the explanation you will be forced to realize that, okay, here I missed an assumption, or here I did something wrong. This doesn't actually make sense. Okay, thank you very much, rubber duck. But you can bring an actual rubber duck for this person, for this purpose, sorry. You have an actual living person, and when we are doing this, especially during like the last hour of the contest, when it may be the case that one of the team members has nothing better to do, so helping debug is the way that maximizes the expected profit. The mental trick with it is very simple. When your teammate is trying to explain to you what he's doing in the code and walking you through it and showing you what they are doing, you need to put yourself into the mindset, this person is an idiot. They are your friends, so it is very easy. So you look at that, and you have to think to yourself, this person is an idiot. Why do we do this? Why does this help? Well, because it's very easy to become complacent. If you think, you like your teammates, right? Usually it happens that you like them, and you think they are smart. They are almost as smart as you, right? So it's very easy to become complacent, and when they are telling you this and that, here I will sort this, here I will go through the entire list and that list, it's very easy to trust them. It's very easy to like say, yes, yes, this makes sense, that makes sense. And then you reach the end of the code and both of you are like, I don't know why it doesn't work. Everything looks perfect, you are smart and we are happy. No, if you think your teammate is an idiot and you are trying to catch him at each and every of those steps, this is much more difficult for you because you have to focus and you have to mistrust them at each and everything they are saying. Each and everything has to be scrutinized, and you need to think like, does this actually make sense, or is he saying something that is completely stupid and I can laugh at him? Yeah, this is completely stupid. And if you put yourself successfully into this mindset when listening to somebody else explaining their code, it's much more likely that you will actually catch the mistake and not fall into the mode when you are just nodding your head and playing the rubber duck. Okay. So let's switch it up again. I will talk a bit more about things that are more context related later, but let's do some actual computer science for a while again. And yeah, right now I can, for example, show you one past World Finals problem. This one is approximately 8 years old. And on this problem I will illustrate what to look for in many of the actual World Finals problems. So in this particular problem we have the following setting. There is a graph, a directed graph. One of the vertices of the directed graph is special. This is headquarters. And there is a bunch of other vertices somewhere in the graph. And there are paths between those vertices. So these are the individual offices of the company. And you have a collection of directed edges between them. And the collection is such that the entire thing is guaranteed to be strongly connected, so you can get from everywhere to everywhere along those edges. And each of the edges has some specific length. And now what we want to do is we want to divide all of the offices, not the headquarters, just the offices, into an exact number, G, of smaller groups. So, for example, we can say that these two offices and this one will be one of the groups, and these two offices will be another group. And once the offices have been divided into groups, then the offices within each group will have to communicate and send couriers between each other. And the couriers always have to go through the headquarters of the company. So if there is a courier going from here to there, they will follow this path, first to headquarters, then to the other vertex. And if there is a courier going from here to there, they will first reach the headquarters along the shortest path, and from the headquarters, then they will reach the other vertex. And you need to do this for each pair of the vertices that are assigned the same group. And your task is to find the distribution of offices into the given number of groups in such a way that the total travel time of all of the couriers is minimized. So this is an example of a World Finals task that got solved during the contest, not during the first hour, but reasonably soon during the contest. And it got solved by a bunch of teams. So it is not the easiest one in the problem set, it is not the hardest one in the problem set, it's somewhere in the middle. And quite a lot of World Finals tasks will be of this particular type, that none of the steps from the statement to the solution is horribly difficult, but there is a lot of them, and you need to work through them. And quite often, at the last hurdle, you will still get some surprise that you need to do something more smarter than you expected it to be. So, what is the obvious part of this particular setup? Well, the obvious part is that we don't actually need all pairs shortest paths in this graph and computing them using the standard algorithm because of the requirement that all of the couriers are always going through the headquarters. So for each of the pairs of the vertices that will end up in the same group, you can break each of the paths into path from the vertex to the headquarters and from the headquarters to the other vertex. In other words, any single vertex, if we know the size of its group, what will happen is that this particular vertex will contribute, if there are k vertices within this group, then this one will send k-1 couriers out, and all of these k-1 couriers will go to the headquarters, and it will also receive k-1 couriers from the other vertices, and all of those will come from the headquarters. So all we need to pre-compute are the distances from the headquarters everywhere, and then against the direction of the edges, distances from everywhere to the headquarters. So we run Dijkstra twice. We have pre-computed these distances. And now for each vertex, we have a single value, the sum of the distance from the vertex to the headquarters and the distance from the headquarters back to this vertex. We can forget about the entire graph, and the rest of the solution can only work with these distances because we already have all of the information we need. So now we have the list. For each vertex, we know the sum of the distances. And now we are going to divide the vertices into the groups. So one natural thing to do is to sort all of the vertices by this sum of the distances from there to there and back again, so that we have something like this.
What are the bounds of the problem? Like the size of n, the size of
the bounds are such that n squared fits very comfortably into the time limit and cubed dies out. Or n times g times something, so g can be up to n, so that's the worst case that can be there. Okay, so without actually dealing with the exact numbers, let's try to come up with an asymptotically as good solution as we can, and then I will stop at the moment that was already good enough for the limits in this particular Watt finals. So now the main question is, given this array of sorted lengths, how long it takes there and back again, and the number of groups, how do we find the optimal division of the vertices into those groups? And again, our intuition is probably telling us that we should group some similar vertices together. How do we prove such a thing if we have such an intuition? A very good technique for all kinds of combinatorial optimizations is thinking about a single edit. If you are given any task where you can, for example, find the optimal order in which to do a sequence of n actions, a very good way of finding whether or not a greedy solution exists at all, and if it exists, what exactly is the greedy criterion, is imagining that you have the sorted order already, and thinking about what happens if you swap two consecutive elements of the sorted order. Not just any two elements, it is enough to think about swapping two consecutive elements, because if there is any greedy criterion, like for example sorted based on the ratio of value A and value B, and if the sorted order is the optimal one, then any order that is not optimally sorted will have two consecutive elements that are not sorted according to the property. So any order that is not optimal can be improved by making a local swap, and the local swap will usually do a very small change to the actual value of the solution, because it will often influence only the elements that are actually being swapped and nothing else. Like if you are optimizing, for example, some scheduling on a processor, and each of these individual items is a job that takes some time to complete, then completing job A and then job B, and completing job B and then job A together takes the same amount of time, so nothing else before or after that is influenced by this. And thinking about these small local swaps and what is their effect can often give you the whole solution. And a similar thing is going on here. So imagine that you have a bigger group that looks like this, and a smaller group that looks like that. What happens now if we take the most expensive item here and the cheapest item there, and we swap them? So this one will go to the red group, this one will become a part of the blue group. So within the red group, this 15 was paired with two other offices. So we paid the 15 twice, once to send a courier to this office and back, once to send a courier to that office and back, and we were paying this 34 4 times to send couriers to all of those. And when we make the swap, we will pay the 34 twice, and we will pay the 15 4 times, which is definitely cheaper. So whenever you have a bigger group and a smaller group, you want all of the values in the bigger group to be smaller than all of the values in the bigger group. So if I already told you what are the optimal group sizes, then you know how to produce the optimal solution. You will take your group sizes that I just told you, you will order them from the biggest to the smallest, and this will be how we divide the input. The first 5, if the optimal group sizes are 5, 2, and 2, then the first 5 will be the first group, the second 2 will be the second group, and the last 2 will be the last group. This will be the optimal division. So now we know that in the optimal solution, the input array is divided into contiguous segments that will become the groups, the actual groups of offices in the solution we are supposed to produce. And now we could do dynamic programming, and this is the moment when you think you have already solved the task, and then you realize that this is still quite, by some factor, this is exceeding the time limit. So if you just use the information that the groups are consecutive, you can do dynamic programming that looks like follows. For each prefix of the sequence, so for each A, the length of the prefix, and for each B, the number of groups, you will ask the question, what is the optimal way of dividing this prefix into exactly that many groups? And you can answer this question by going through the input and try all possibilities, for example, for the last cut, to say which part is group B, and then you ask recursively the question, if this is the group B, I can easily tell, as I'm increasing it, I can recompute the current cost of this particular group, and to this particular cost, I can then add the result of the recursive call, what is this optimal way of dividing the rest into B-1 groups. So if you do this, and you try all possibilities for making the cut always, then your time complexity will be n squared times g, and if g can be arbitrary, this is n cubed, because the number of questions you are asking is n times g, the length of the prefix has n possibilities, the number of groups you are cutting to has g possibilities, and for each of those questions, you are trying out n possible ways to make the cut. So this is too slow to get accepted, but only slightly. We need to come up with one final optimization. And as I was saying, this is what you can expect from a world finals level problem, that sometimes there will be this extra step. You already know exactly what you want to do, but you need to come up with a smarter way of doing it. And in this case, the smarter way of doing it is to realize that the bit we knew about and forget about and never used is that not just it is the case that the groups have contiguous segments of the array, it is also the case that their lengths are non-increasing. So when we are cutting this particular piece of the array, this particular prefix, for example, into 3 groups, then we know that the length of the third group can be at most 1/3 of the length of this segment. So we don't have to try all of these possibilities for the size of the third group, just all of these possibilities. Yes. So when we are imagine a specific prefix now, we have a fixed prefix, and now we are going through all of the possibilities. So when I'm trying to divide it into one group, it's just a one group. But I will spend the actual linear time in order to compute the total cost of the group if I haven't recomputed it. I can do this because it will fit into time and memory. When I'm trying to divide it into two groups, I will start at the end, and I will try possibilities only up to here. So only half of the array I will traverse. When I'm trying to divide it into three groups, it will be 1/3 of the array, then 1/4, 1/5, and so on. And as I was saying, sometimes the source of a log n in time complexity is a harmonic number appearing somewhere, and this is exactly one of those cases. So if we sum up the work for this particular prefix of the array, it is its length plus its half plus its third and so on. So it's the length times the logarithm of the length. And this improves this n squared in the time complexity to n times n, and you get accepted. So this is the anatomy of an ordinary middle-level world finals problem. That none of these steps is that horrible. Seeing this particular trig is probably the nicest bit of the problem, at least for me, because it's so original. But none of the steps is impossible to do. So individually, each of these steps would be on the level of most world finals participants. And if you were set a problem that would be condensed to just the single step, then many more of the contestants would get it. But just like going through the entire sequence of those steps takes time, and it takes somebody sitting down with a pen and a paper and playing around with the problem and thinking about the problem before you get to the stage where you understand all of the steps and can actually implement a working solution. Okay. Now let's get back to a puzzle. I like puzzles, especially combinatorial and algorithmic puzzles, because they are kind of the same type of practice, but for us who are lazy to write code. So this particular puzzle is a puzzle that has, for example, appeared in a very nice paper that was presented at one of the conferences gathering for Gartner, I think. And this is a paper titled 7 Puzzles You Think You Must Not Have Heard Correctly. And this one is the most stunning out of them. And this is a puzzle sometimes called Names in Boxes. So, as in many of these puzzles, this is a puzzle about, let's say, 100 prisoners, and somebody playing a cruel game with those prisoners and giving them a chance to be free. And this particular game is played as follows. There are 100 boxes. And the boxes are guaranteed to be laid on a table that has a left end and a right end. So there is a wall behind the table. There are 100 identical boxes in a row on the table. The 100 prisoners are currently in a courtyard. All of them sit together. They can talk to each other. They are told the rules of the game as I'm explaining them to you, and they can devise a strategy together. And what the warden is doing in the meantime, the warden has 100 pieces of paper, each with the, let's say, unique email address of one of the prisoners, or another unique identifier. So 100 unique identifiers, names of the prisoners for short. And the warden will take these 100 names and place one of the names into each of the boxes, shuffled uniformly at random, or whatever. The warden doesn't even need to shuffle. They can use whatever strategy they like to place the names into the boxes. And now, one person at a time, the prisoners will be led into the room with the boxes, and each prisoner is allowed to open any 50 boxes. And the prisoner can do this one box at a time, so they can open the first box, pull out the paper and read it, open the second box, pull out the paper and read it, and so on. And the goal for each of the prisoners is to try to find their own name. If they do find their own name within the 50 boxes, then they are led to a different room where they are gathering the prisoners that have already taken part in the experiment, and everything is fine. As soon as any one of the 100 prisoners fails to find their own name within the 50 boxes that are open, the entire game is over and everybody has lost. So just to make sure that you understand the problem, I will now explain the two possible strategies for the prisoners. Possible strategy number one. Each prisoner will just come into the room and open the first 50 boxes. What happens then? Yeah, it is a guaranteed loss because at most 50 prisoners will succeed and find their own name, but as soon as one of the prisoners whose names are in the other half of the boxes comes into the room, if they use this strategy, they will not find their own name and they have all lost. Another strategy, and it seems to be like the only strategy that you can reasonably use in a problem like this, is just to open the 50 boxes uniformly at random. So whenever you are a prisoner that comes into the room, open random 50 boxes. This guarantees you a 1 in 2 chance of finding your own name, so 50%. So the first strategy has probability of success 0. What is the probability of success of the second strategy?
1/2 to the power of 100.
Yeah, 1/2 taken to the power of 100, which for all practical purposes is 0. It is not exactly 0, but it is almost 0. Like when we are doing any kind of randomized algorithms anywhere, probabilities much bigger than this one are still okay for us to say that this is something that never happens. Like realistically, when you think about a computation, for example, when we are generating some random primes for an RSA private key, and we are using not a deterministic primality test, but we are just using some rounds of Miller-Rabin and checking whether it is a prime with a very high probability. If the chance of being wrong with this algorithm is less than 2 to the minus 40, for example, then it becomes, we are getting to the territory where a chance of a hardware error during the computation, when we are actually doing it on a physical computer, is more likely than the chance of the software error or of being in the very unlucky case of getting all of the false positive reports. So yeah, like a very good like rule of thumb for this is something along the lines. So if you want to estimate like hardware errors, imagine that what happened to you when you owned your personal computer. Like probably once every few years there's something that dies within the computer. And yeah, from this you can make an estimate of how frequent the hardware errors are. You can have like hardware errors of the type that your computer got hit by some stronger cosmic radiation and it flipped a bit somewhere in your RAM or something along those lines. And yeah, this happens very infrequently, but you can push the software error very easily below this hardware error by just running more iterations of the algorithm, and this as a type of error is much below those. Well, in fact, when I was talking about your computer burning out once every few years, this is also relevant not just when it comes to probabilistic algorithms, this is also relevant when it comes to distributed algorithms. If you are running something on a cluster of 100,000 computers, if every single one of them will die eventually, on average once every few years, how often does a computer in your 100,000 strong warehouse die? And suddenly it turns out to be the case that computers dying during the computation is something you have to count with if you are computing stuff on this massive scale. Or at least you need to have a layer inside your stack that is dealing with the individual computers dying and still allows your entire computation to go through. So there are many fun challenges that come with hardware in non-reliability. in the real world. But let's get back to the puzzle. So we have two strategies, one with probability of success exactly 0, and one with probability of success practically 0. But this is a puzzle somebody actually set us, so there has to be something we are missing. There has to be some trick in the setting of the puzzle. And there is no trick in the setting of the puzzle. You understand the puzzle correctly. And there still is an actual solution with a much, much higher probability of success. In fact, you can push the probability of success to somewhere like 30-ish%. How does one do this? Imagine, if you will, that like in every good programming competition, instead of having names, the prisoners are numbered from 0 to n-1, and these numbers appear inside the boxes. What the prisoners can do in their own heads is that as the locations of the boxes are fixed, they can also agree on the numbering of the boxes themselves. So this is box 0, this is box 1, box 2, box 3, all the way through box n-1. So when the warden places the names into the boxes, they are creating a permutation. And the permutation can be broken into cycles. And the cycles are the idea to a good strategy for this particular problem. So if you are a prisoner number x, what can you tell about the particular cycle that contains your own name? The cycle contains the name x, so the cycle also has to contain the box number x. So your first action is opening box x and reading the name inside the box. And if the cycle has length 1, what just happened is you have found your own name and you win. If the cycle has length 2, you will find some other box, so box x2. So you go there, open box x2, eventually there you may find some number x3, and then you open box number x3, and you have found your own number. So in this way, you always read a new name from the box and open the box with that specific name on it. In this way, you are following along the cycle that contains your particular name, and eventually you will reach it. If you would if there would be no limit on the number of boxes you can open, then you would definitely, if you are following this process, you are going along the cycle. So, for example, if your own number is 7, and box 7 contains the number 5, and box 5 contains the number 12, and box 12 contains the number 7, this is one cycle. The permutation is then 3, and you have found your own name once you get to the end of the cycle. So the limit 50 now comes into play. And now the question is, what is the probability that everybody wins this game? And if the permutation inside the boxes was chosen uniformly at random, and either the warden does this or the prisoners can do this themselves by numbering themselves uniformly at random. So if we can have guarantee that the permutation was chosen uniformly at random. And when do we win? When do we lose? The prisoners win if none of the cycles of the random permutation have a length of more than 50. The prisoners lose if there is one single giant cycle that contains more than half of all of the elements. And you can do the math on this. What is the probability that the random permutation contains such a big cycle? And you can turn the probability into combinatories. What is the number of permutations with big cycles? And it turns out that as n increases to infinity, there is a constant fraction of permutations where there is one big cycle, and everything else has only smaller cycles than half of the permutation. And the ratio of the sizes of one of these two sets is converging towards, and you guessed it, 1 over e. Yeah, there is always e when you are dealing with some special floor permutations. So it turns out that with a reasonably high probability, the random permutation will not have any long cycles, and then all of the prisoners will follow, each of the prisoners will follow their own cycle. Each of those cycles will be shorter or equal to 50 in length, and everybody will get saved. For a final bit on this puzzle, even if you already knew it, here's an extra question for you to ask. Suppose that in addition to the setup we had previously, there is also a cleaning lady, and the cleaning lady has been bribed by the prisoners, and she has enough time to go into the room, open 2 specific boxes, and swap their content. Given that the prisoners can instruct the cleaning lady to do this, how does this increase their chances of winning the puzzle? And I will not give you the answer, but I trust that you can come up with the answer on your own. So if you can examine the permutation, this is an important bit I need to stress once more. So the cleaning lady can look at the permutation, and based on the permutation she sees, she can make the swap.
Only one swap?
Only one swap. Okay. If you fail to solve this, then just ask me, let's say tomorrow, and I will reveal the answer. But yeah, I think it should be reasonably easy to solve. Okay, and before the break, let's do one more thing. So I will show you one more task. And in this case, it's a combination of 2 things I like. ¿Por qué no los dos? Tak. So this is a problem I actually learned in 3 different ways. This is a problem I learned first when I was playing around with doing magic tricks. This is a problem I encountered a second time as a mathematical puzzle in some collections. And this is a problem I encountered a third time several years ago at the World Finals, when somebody used the problem to write a World Finals problem. And essentially the idea was still the same, and it was used to solve this particular World Finals problem. And this problem is about the magic trick that was devised by mathematicians and magicians by the names of Fitch and Cheney. And it looks as follows. In the original setup of this magic trick, we have a standard poker deck of 52 cards, so hearts, spades, clubs, and diamonds, and from ace through king. This deck is handed off to a spectator. The spectator can freely shuffle the deck, and while the magician is absent, the magician is locked in a box where they cannot hear or see or whatever, interact with the surroundings in any way. The spectator will select 5 of the cards from the deck uniformly at random, or in whatever way they like, and they will hand off these 5 cards to the magician's assistant. And the magician's assistant will do the following. So they will place 4 of the cards visibly, and 5th card will be hidden. So we can see 7 of hearts, a 3 of hearts, a 2 of clubs, and the king of diamonds, for example. And now the magician is released from the hermetically sealed box. The magician comes to the table, correctly names the 5th card and flips it, and everybody applauds because the magician got it right. Okay, so what's going on with this trick? Clearly, some communication is happening, and in particular, the assistant can choose the order of these cards to communicate to the magician what is the 5th card. But, let's actually do the math. So what we have here is 4 cards. If we can agree in advance, the magician with the assistant can of course agree in advance on the actual ordering of all of the cards in the deck. Usually what is done is, for example, take the ordering from some standard game like bridge. So you have the alphabetical order of suits, clubs, diamonds, hearts, and spades. are from the weakest to the strongest, and then you start from 1, which is the ace, 2, 3, 4, and so on. So you can say that now this is the smallest card, second smallest, third smallest, and the biggest in the deck. And this gives you lexicographically one of 24 possible permutations. So the magician can tell between 24 possibilities.
But you can also choose
Which card?
Yes, yes. That's exactly the point. So this is the point where when the trick actually stumps also some of the mathematicians, because there seems to be a missing bit of information. The standard deck has 13 cards in each suit, 4 suits, for a total of 52 cards. So 4 of them are here. There are 48 cards left, and there are only 24 possibilities within the permutation. So there seems to be a bit of information missing. And of course, the magician and the assistant can cheat, and you can do this trick by transferring the bit in some other way. But it is possible to do this trick by the assistant arranging the cards, and then you lock up the assistant, remove them completely so that they cannot communicate in any other way, and only then you will release the magician. And there is a way to transmit the extra information needed to be able to identify this card perfectly. And as the guys in the front row said, the main trick, the main bit that we are missing is that the assistant is not forced to hide one specific card and then arrange the other 4. The assistant can choose which of the 5 cards will be the hidden one, and then arrange the other 4. And the possibility of this choice gives them a better strategy. And the way this trick is traditionally taught to budding mathematical magicians is as follows. So you have 5 cards, you only have 4 suits. Very simple pigeonhole principle. You need to have at least 2 cards that share the same suit. Now you can imagine all of the values in the deck on a circle. So we have ace, 2, 3, 9, 10, jack, queen, and a king. And you can choose 2 specific cards of the same suit. Let's say like here we could have. Now let's choose a completely different card. So let's say we have chosen the 2 of diamonds and the jack of diamonds. So the 2 of diamonds is here, and the jack of diamonds is there. And as we are going in the clockwise direction along the circle, the entire circle is 13 steps. So either this distance is at most 6, or this distance is at most 6. You cannot have both distances bigger than 6, because at least 7 plus at least 7 is at least 14. So what you do is you choose this card, the one that is at the beginning of the shorter segment, to be the first one visible. You choose this card to be the hidden one. So you would be doing that the jack of diamonds is the visible card, the 2 of diamonds is the hidden card, and now you have the remaining 3 cards. And what you need to use the 3 cards for is you need to encode the distance, which is now a number between just 1 and 6. And conveniently, you have exactly 6 options for the permutation. So by choosing the permutation of the other 3 cards, you can encode the distance between 1 and 6. And the magician then looks at the first card. They know that the hidden card is diamonds. They will examine this permutation and see that this is the 3rd of 6 possible permutations. So I go from jack to queen, king, and ace. This is the 4th one. I go to the 2, and so on. So this is how the trick is normally performed. And this is a strategy that is very easy to learn, both for the magician and for the assistant, and actually execute during a performance. So if you are doing some lectures for younger contestants in the future, this is something you can actually do for them if there's 2 of you, and then have them analyze it on their own. But the actual nice thing about this particular trick is that it doesn't end here. What we have just seen is a strategy for the magician and the assistant that exactly works with this deck of 52 cards. And now we are using everything. We are using the choice of the last card, we are doing it the smart way, and we are using this entire permutation, which has exactly the amount of freedom that we needed for the solution to work. So it feels like this is at the actual limit. that 52 is the biggest deck of cards with which you can still do the trick. If you had two such deck of cards that have distinguishable fronts and backs as well, so you can tell that this is a 7 of hearts from the first deck and this is a 7 of hearts from the second deck at a glance, you could still do this trick. If you had 120 something cards, you can still do this trick. The limit where the trick fails mathematically is much, much bigger than the 52. And this strategy I have just shown is far from being optimal. It's just that it's still the only easy to describe strategy we have, and for all of the others are much more complicated. So what is the underlying math, and how can we guarantee that the strategy still exists, and the robotic magician and the robotic assistant could actually still play the game with a much bigger deck of cards? So what's going on here is that you can actually imagine a very, very large bipartite graph. And in a bipartite graph, on one hand, are the observations shown to the magician. So from the deck of n cards, you choose a sequence of 4 cards. So each possible sequence is of 4 distinct cards will be one of the vertices in the left partition of the bipartite graph. And on the other side, you have, and choose 5, you have all possible 5-card subsets. And now a valid strategy for this game corresponds to what? The valid strategy corresponds to a matching between these two partitions. And of course the matching is such that whenever you have a 5-card subset, the possible edges that are leading to this particular vertex are connected only to the 4-card sequences that are using 4 out of these 5 cards. So for each possible 5-card subject, 5-card subset the spectator can give you, you need to choose, if I'm given this particular subset, what sequence of 4 cards I am going to show to the magician. And of course, the magician must be able to see this and uniquely determine the actual 5-card subset, so to determine the missing 5th card. So you cannot have 2 different subsets assigned to the same sequence. So what we are looking for is a matching that is completely covering this particular partition. There is an obvious necessary condition, which is that if this partition is smaller than this one, then such a matching cannot exist. And at some value of n, this will actually happen. And the opposite side of the coin is that in all other cases, and in particular I think that for the value of n that is the maximum possible, there is an actual exact equality. It happens to be the random case, but even if it weren't, in all of the situations we can actually find a matching between those two sets that is covering the smaller of the 2 partitions. Why is this the case? Well, the thing you need to realize about this particular bipartite graph is that it is actually in some sense irregular. So what's going on here is that for each of these 5-element subsets, the number of outgoing edges is exactly the same, because this is the way of selecting 4-card sequence out of 5 cards. So each of these vertices has exactly the same degree, each of these vertices has exactly the same degree, and you can remember a result about matchings in bipartite graphs called the Hall theorem, that is exactly talking about situations similar to this one, that if you have so the Hall theorem is giving us both a necessary and a sufficient condition for a perfect matching to exist, and it is telling us that if you select any subset of one partition and take all of the nodes that are connected to at least one of these, you must have at least as many nodes on this side than on that side. It is obvious that this is a necessary condition, and the main part of the theorem is that it is not just necessary, but also sufficient. If this is satisfied for all possible subsets, then this gives you a way to construct the actual perfect matching. And you can also generalize the theorem very slightly to handle with this particular, like this is a slightly bigger generalization. So if you have regular graphs, you can show that as a consequence of Hall's theorem, there is always a perfect matching. And if you have this kind of regular on one side and regular on second side graphs, you can show that as a consequence of Hall's theorem or the proof of it, then you can always have a matching the satellites, the smaller of the two halves. So for any n, for any size of the deck, you can examine how many 4-element sequences there are, how many 5-element subsets, and if this one is smaller or equal to that one, then you can still do the magic trick perfectly, and any specific perfect matching or matching that covers this entire partition is the strategy the magician and the assistant can use. So there is not a 52 card limit, there is a 120 something card limit where this particular thing breaks. Okay, so, and as I was saying, I think in 22 at the World Finals, I think the most recent that actually took place, they had a problem that was essentially coming up with this math and then doing something else extra on top of it. Because as I was saying, the World Finals problems will be usually we're having an extra step of slump complications. In this case, the extra step in the problem, if you look it up, is that there can be markings on the other sides of the cards. Yeah, well, if you are interested in that full problem, find the World Final statements, read it, and if you then are interested in a solution for that full problem, look it up on YouTube and you will see me explaining the full solution. So. All right, we are past 10 o'clock, there's probably coffee outside, let's take a break. I will talk to you about a few more problems I have written for several different, like, top-level competitions, and the reason why I still remember them and like them. And the story of one of these problems begins with a very, very simple puzzle. And the puzzle is as follows. So we have our planet Earth. The planet Earth has an equator. And everywhere on the equator there is some temperature. And the puzzle is asking you to show whether or not there have to be 2 points that are exactly opposite each other on the equator that have the exact same temperature. Is this always happening or not? And if yes, why? If not, why not? And the answer to this puzzle is very easy, but it is a useful trick, again, to have in your repository of tricks. And the answer is as follows. So the hidden assumption behind this question is that a temperature is a function that is defined in every single point around the circle. And we will assume that the function is continuous. So the temperature doesn't have huge jumps. If you move by an epsilon, the temperature can only change by an epsilon. And now imagine that we measure the temperature at one specific pair of 2 antipodal points, and we will get their temperature here is minus 12 Celsius, and the temperature here is minus 15 Celsius because we just happen to hit some cold weather. So, but if this is an equator, then yeah, it's not likely, but it's probably positive. But it doesn't matter. It may be the case, of course, very, very highly unlikely, that we already hit a pair of points with the same temperature, but almost certainly we will hit points that have opposite temperatures. So now we can imagine that there is a boy standing here, and that there is a girl standing over her there. So she has a skirt, and gravity, luckily, works for her. So the skirt is actually pointing downwards. And now they both start at the same pace, walking around the Earth, until they trade places. What happens then? And imagine that the time is frozen, the temperature doesn't change over time, and we are just moving 2 pointers and examining the temperatures in this specific moment in time. At the moment when we started, the boy was seeing the temperature 12, the girl was seeing 15, so the girl's temperature was 3 higher than the boy's. And as we are moving around the Earth, when they swap places, the girl is here, the boy is there. So the difference between the temperatures, girl minus boy, in the beginning it was +3. At the end of the process, it is -3. And this means, due to the temperature being continuous, the difference between 2 temperatures is continuous, and therefore somewhere along the way, there must be the point when the difference between the temperatures went from being positive to being 0, because you cannot get from positive to negative without crossing 0 once. So this is a mathematical proof that at any moment in time, if we assume that the temperature is continuous, there are 2 antipodal points on the equator that have the same temperature. And I was thinking about how do you turn this or something like this into a competition problem. And there have been easier competition problems where you do this thing, for example, in a discrete setting, you can set up something like in every step the function, so you have n actual measuring points around the circle, and between those every 2 the temperature changes, for example, exactly by +1 or by -1, and you want to find such a pair of points. And the thing these problems have in common is that you can solve them by applying binary search. So if you know that here the difference is +3, so this is, let's say, this is angle 0, and the angle 180 is corresponding to the opposite difference, so you know that the actual angle is somewhere between 0 and 180, and you can binary search it, so you can look at the temperatures at angle 90, and if you hit, then you hit, and if you found another case where the girl is still leading, then you know that the answer is somewhere on this segment, and if the boy is already leading, the answer is on that segment. So you can binary search in order to find the place in the continuous setting with any precision that you like. In the discrete setting, you will eventually find the exact place. So how to turn this into a more difficult problem? And a more difficult problem can deal with either more dimensions, I will get there in a moment, or it can deal with more different cuts. And some playing around led me to the following observation. So suppose we have a polygon, and in the story of the problem, the polygon was a birthday cake, and there are 6 people at the celebration, and I would like to give everybody the same amount of cake. So we would like to cut the cake into 6 pieces with equal areas. Definitely for a polygon, it's not an easy question to ask for an equal shape as well, but equal size, this is what we like. And if you want 6 equally sized pieces, you can definitely do this by cutting into 6 pieces, just 6 pieces without requirement on size. Can be done using 3 cuts, right? If you make 3 cuts through the same point, you will get 6 pieces of the cake. If you choose any point inside of the cake and you choose 3 directions for the cuts, you will cut the cake into 6 pieces. And now the question that I was asking in this competition problem, and this was one of the on-site finals problems, was, is it possible to actually choose this point and these 3 directions in such a way that the 6 areas will all be equal? And you can still answer it using just this type of an argument. It will just be more involved and there will be several nested steps. So let's start with an easy observation. So if you choose the direction of any one of the lines that you are using for cutting, the line has to cut the cake into exactly halves. Like, yeah, right, you have the 3 pieces on one side, 3 pieces on the other side. So this particular line on its own has to cut the cake exactly into 2 halves. This has to be true for each of the 3 lines. So if you knew the directions in which those lines are pointing, you would be done. Because for each of the lines separately, you can now use binary search to find the exact point at which the area below the line will be exactly equal to the area above the line. If you put it lower, then the area above the line will be bigger. If you put it higher, then the other area will be bigger. So you can start binary searching between here and there and find the exact spot for the line. So what happens now if you do this? Suppose somebody has helped us and told us the direction of one of those 3 lines. What can we do then? We have already cut the cake in halves. What can we do with the other 2 lines? Suppose I choose another angle for another of those lines, and I find what happens if I cut the cake using this line. There will be a piece here and a piece there. So again, if I can find a position for this line so that it cut the cake into halves. Are these pieces of equal sizes? Not generally they won't. And this will be already bad, so this line is not suitable. So for this particular direction, you are creating a bigger piece here than there. So what might help is rotating this line slightly more in the direction where it makes it more possible. And now, if you think about making maybe like 2 nested binary searches, you can find one point such that you can make a second line that both divides the cake into halves, and this is 1/6, and this is 1/6. Now you can do independently the same thing for a third line, but now it turns out that you can get 1/6 here and 1/6 there, but not by passing through the same point. So you fix this original line, you can solve the second line independently, the third line independently, but the 2 points will generally be at different places, and this will not be a valid solution. But now as you rotate the first line, these 2 points where the solution comes, you will also rotate, and if you rotate the first line full 180 degrees, the 2 points will swap places. And as they are moving continuously along the line as you rotate it, there has to be an angle for the first line at which those two points exactly hit each other. So what you have now is you have not just one, not just two, but 3 nested binary searches. The outermost nested binary search is looking for the angle of this one, and then you use 2 nested binary searches to find this particular line and point, this particular line and point, and compare where they lie. So it turned out to be quite a nasty problem, and it turned out to be solved within the contest by one of the contestants. So it was the right level of difficulty. Writing problems for the very top of the spectrum is incredibly difficult, and if you see after maybe some contests like Trojan finals or World finals of the ICPC, you will probably see some people online on some forums complaining that this problem didn't really work because it was too hard, that problem was too easy. Give the problem authors a bit more respect than that, because it's reasonably easy to set problems for people who are below your level, because you see into what's going on, you know, your knowledge is much deeper than the problem itself you are setting, and you are equipped very well to judge its difficulty and suitability and so on. At the very top, by definition, the best problem setters, but the best authors of competition problems can be roughly on par with the best competitors, but not beyond that. And at this level, it is also the case that whether or not a problem at something like the World Finals will or will not get solved depends on so many other factors. For instance, if you have a problem set where the other implementations are too time-consuming, then the teams can simply not get to that problem, even though in other contests they would be able to solve it. They can be encouraged by the scoreboard to focus on other problems and so on. So there can be many, many different factors that are not necessarily related to this particular problem that will influence its performance in the contest. And also in terms of the actual difficulty for this particular set of contestants, it's not like you have a continuous spectrum of good problems to use. Their amount of problems of this type of difficulty is very limited, and the amount of people who can come up with new problems like this is very limited. So you do the best with what you have got, and you are juggling so many pieces in the air and trying to make the hard contests like World Finals happen that, yeah, sometimes you will get problems that will turn out to be much easier and much harder than you expected, and that's okay. That's still the best we can do, and the problem setters are amazing for being able to do at least that much. Anyways, I promised you multiple dimensions when I was explaining this particular task, and the multiple dimensions is again a bonus question I will ask you without giving you the answer. If you have already heard about the puzzle about the same temperatures on the equator, you may not have encountered that it generalizes, or does it? So, on the entire surface of a planet Earth, which can now assume to be a sphere, we have not only the temperature, which is one function that is changing continuously, but we also have atmospheric pressure, which is another function that changes continuously along the surface of the Earth. And now I'm asking you, is it true that there are always, now not just on the equator, but you can choose anywhere around the surface of the Earth, are there 2 points that at the same time must have the same temperature and the same atmospheric pressure? And this is not an easy question, so don't expect to answer it just off the top of your head right now, but think about it. If you haven't heard about it yet, think about it. Is it true? Is it false? How do you prove it? How do you disprove it? All right. And now for one more problem. Again, this is a problem I have written for the top round of a competition, and this one was solved much more than the previous one, so it's probably a bit easier. And it's also related to something I was talking about in one of the previous lectures. And the problem, in its essence, goes as follows. You are given a number x, and the number x can be up to, let's say, 10 to the 18. You are given a number L, and the number L can be between, let's say, 40 and 120. And your task is to produce any number with the following properties. It has exactly length L, so L digits when written in decimal. And it is divisible by x. So x divides the number, or we can write that there exists some n such that n times x equals this number. So we are looking for a multiple of x that is long and has one particular special property, and this is the core of the problem. If you look at the set of digits used inside the number, there can be at most 4 distinct digits. So for example, you can have a number that has plenty of 5, 7s, and then a 0 and a 1, but as soon as you have used 4 digits, you cannot use a 5th one within the number. So how do you solve a task like this one? And the key observation to solving this task is, well, you can get a general idea from this particular constraint. Like constraints in problem statement are part of the information you get at the contest, and yeah, this is like one of the major differences between programming competitions and, for example, actual research, is the implied guarantee that a solution exists. So when you are given a problem at the contest, you actually know that there is some reference solution that actually solves this problem, and the constraints are kind of telling me what are the parameters of the solution, what to expect from it. And this particular type of constraint isn't that common. So you have something like 10 to the 6 if you expect a linear solution, or 10 to the 18 if your solution shouldn't really depend linearly on this particular variable, at most logarithmically or something like that. And 10 to the 11 is something that is reasonably infrequent and usually suggests that you are doing something with a square root. The square root of 10 to the 11 is below 10 to the 6, somewhere between 10 to the 5 and 10 to the 6. So square root of x is a reasonable amount of steps. Of course, blindly following the constraints in the problem statement is not always a winning strategy. In particular, in my problems, I often, if I don't really care about particular constraint, then I will make it on purpose smaller. And I have set problems, for example, that do have a linear time solution. And I set the constraints so that it seemed like the expected solution is quadratic. And it made the problem much harder because nobody was looking for the linear solution. And they were trying to come up with a solution that would match the constraint and another solution that would match the problem itself. But in this case, I'm not deceiving you, there is something with the square root going on.
Can you restate the problem? I think I didn't understand.
Okay, one more time the statement of the problem. The input you are given is just these two values, the x and the L. And we are looking for the number that has 3 properties. It has length exactly L, it is a multiple of x, and if you look at all of the digits used inside when writing down the number, there are at most 4 distinct among them. So for example, you can use the digits 0, 1, 2, and 3 to write the number, but you cannot have any 4 in the number itself. So let's imagine that what we can do is we can try to use this, to solve this task completely by luck. So let's pick any set of 4-digit lengths, and then generate a random number of this length, and compute what it does modulo x. And of course, the probability of hitting is only 1 over x. It can be even smaller because in some cases the remainders modulo x are not actually uniformly distributed when you are generating a random number. But it will not be higher than that probably. Or at least there will be definitely inputs where the probability is roughly 1 over x, if x is a prime or something like that.
Sorry, aren't there only 10 numbers that accomplish the first two constraints? Like if you multiply, you have some multiple of x that has L digits, you multiply it by 10? Oh no,
No.
totally wrong. This is what I was misunderstanding.
Yeah. So all of the yeah, this is 10 to the L.
I see.
So these numbers are between 10 to the L and 10 to the L plus 1.
Yeah.
And if you divide both of those bounds by x, you get the range for n's.
I see. Now.
So there is plenty of n's within the range.
Yeah.
So back to what I was saying. If we generate such a number at random and compute it modulo x, we will get some remainder. If we are very lucky, we will get a 0, but we probably shouldn't count on it, and we definitely shouldn't count on getting it within the time limit. Because this is hundreds of steps per one number, so we can generate at most like 10 to the 6, 10 to the 7 of those, and we will already be running close to the time limit. But there is one important observation and one important property that you can remember from a previous lecture, and this is the birthday paradox. One thing that you should expect to happen reasonably early is that as you are generating various random numbers and computing the remainder modulo x, then reasonably soon, roughly around the square root of x such attempts, so within the time limit, you should get two such numbers that will hit the same remainder. And this is actually how I have written the task, and this is actually the intended first step of the solution. So I did want to write a birthday paradox task with a randomized solution, and this is the setting I came up with when writing such a task. So yes, this is what we are going to be doing. We are going to be generating some random numbers. For now, let's not focus too much on what type of random numbers they will be. We will be generating some random numbers. We will be computing for each of them the remainder modulo x, and we will be happy when we hit two such numbers that will give us the exact same remainder modulo x. And given the birthday paradox, this should happen within maybe 100,000 or definitely under 1 million such attempts, so we can afford to do this. There is one moment where we should stop and think about a little bit. When I was doing the standard analysis of the birthday paradox and showing that for the kids you can compute the probabilities that the first person has a unique birthday, this always happens, then the second person must have a birthday different from the first one, and so on. And from this particular formula, you got the estimate of the roughly square root when you did the math in general. But in this case, it is not guaranteed that the distribution of the remainders modulo x will be uniform. Does that matter? And the answer is that it doesn't, and it also doesn't matter in the original birthday paradox. The uniform distribution of the birthdays is the worst case. If everybody is born on the same day, then as soon as you have two people in the room, then they will have the same birthday. And if there are biases, the biases are only helping us, because if it's more likely to be born on one day and less likely to be born on the other, then the probabilities of getting a hit are higher than they would be for the uniform distribution. So the uniform distribution is actually the worst one, and if there is a deviation from that, it is only helping us to get a collision faster. So we are guaranteed in any setting, under any probability distribution, to hit a collision with high probability by the square root of n bound. So now we are almost there. We now need to think about what we will do next. So we have generated a number a and the number b such that they give the same remainder modulo x. and both have the correct number of digits. Now if you take difference, a minus b, or bigger of the two minus the smaller of the two, this will be the number that is divisible by x. And now our goal is to make sure that this number has the two properties we need. So first of all, the number a minus b needs to still have exactly L digits. And second of all, it needs to have at most 4 distinct digits. How can we get both of these things? One of them is reasonably easy. So if a and b happen to be very close to it, so this has L digits, this has L digits, the difference between them has at most L digits. And if it happens to be shorter, so if you had a and the b of this length, a minus b, and this is the result you got, and it is shorter, then instead of having the zeros here, you can put extra zeros there. And if this was already a multiple of x, then this is definitely also a multiple of x, and it has the correct length. So if you get a shorter number, it doesn't matter, you can pad it with zeros, as long as 0 is one of the digits you are actually using in this number. And for the final trick, how do you make sure that the difference between those two numbers has at most 4 distinct digits? The trick is that when you are generating the numbers a and b, you will be only using the digits 0 and 1. So we are in base 10, but we are only generating numbers that look like this. And as soon as we hit two numbers that give the same remainder, modulo x, and we compute their difference, what you can show that 1s minus 1s will usually produce zeros, zeros minus 1s will usually produce 9s, and the only other digit, except for 0, 1, and 9 that can appear sometimes, is an 8. So you can find some configurations where there will be an 8 because of a carry and something combining. But you can easily show that regardless of the patterns of 1s and zeros here and there, the difference will actually contain only the digits 0, 1, 8, and 9. And as we have zeros, then padding with zeros works as well. So this is how a problem on birthday paradox can look like at the top level of a programming competition. So the biggest conceptual step needed when solving this problem, and this is a step that this was around for the top 8, and 5 of the 8, I think, if I remember it correctly, actually solved the problem during the contest. So first of all, you need to make the conceptual leap of faith that yes, there can actually be a problem with a randomized solution intended and not a deterministic one. And then you need to start thinking in terms of the birthday paradox and going through the steps. Most of the steps afterwards, once you can come up with the idea of maybe I can use birthday paradox, most of the steps are reasonably easy. This trick with zeros and ones or something similar is something where you need to play around and experiment a little bit. But other than that, then you can get to the finish line reasonably quickly. Okay, yes.
What's the name of this problem?
This is called 4 distinct digits, and it's one of the past TCO opens, I think was the contest. I can share the link to it somewhere in the chat or something like that. Okay, one last thing I wanted to talk about this problem is that you may be drawn to trying to do something along the following lines. So maybe there could be some kind of also a meet in the middle deterministic solution, question mark. Like if you have 40 digits, you can solve it for 40 digits by splitting it into the top 20 and the bottom 20. And then if you have more digits, you can just pad it with zeros somehow, as we did before. So maybe this is a promising direction, but in this case, it doesn't work. And the reason why it doesn't work is also quite instructional when we are learning about birthday paradox. So the way that this is set up is getting the actual collisions. And what you would need in the meet in the middle, you would be generating some first halves and some second halves, and you need the first half to match with the second half, so you don't need the same remainder, but you need a complementary one, the one that together with your first one will give you exactly 0 or exactly a multiple of x. And getting such type of remainders is no longer guaranteed if you are, for example, doing it at random, and you cannot afford to actually go through the entire space because it is still too big. So it is possible to get such a solution accepted, but it will require much, much more of like tweaking and playing around with constants and making sure that you can actually traverse some whole space, and at the same time the space is already sufficient to cover all solutions. So I'm not saying this is a blind alley. There are solutions that can be made from these ideas, but they are much, much more painful to implement than if you come directly through the birthday paradox. All right. So now we had a bunch of the hard stuff, and for the next topic I will talk about today, I can again pivot to something that is algorithmically easier, but much more practical. When I was talking about shortest path and mentioned the A-star heuristic that can sometimes be used to compute the shortest path more efficiently by just like expanding those nodes that look most promising instead of those that are closest to the start, as the regular Dijkstra's algorithm does it. I mentioned that there were some kinds of algorithmic optimizations that were making it work reasonably well for routing on static maps. And I will now talk to you about two such optimizations. And this is something that you can still do on your home computer. So, for instance, you can go to OpenStreetMaps, and OpenStreetMaps allow you to download the actual map data for any region. So you can download the entire Europe, and you will have a graph that has maybe 10 million vertices and several tens of millions of edges. And on this graph, we can now look for shortest paths. And you can actually program your own machine to do this very, very efficiently by using A-star and applying some heuristics on pruning the search. And one of the algorithmic ideas, and this is something that was actually used in some of the practical implementations of map routing before we got dynamic data and traffic information in real time and stuff like this. So as long as we are looking for shortest paths and getting from A to B as quickly as possible on static road networks, then this is something that was really used in practice. And we will have two separate optimizations. One of them will be an optimization called landmark heuristic. And this is an observation that looks like this. So suppose there is point A and point B, and I'm interested in traveling from A to B. And somewhere completely unrelated to those 2 points in the road network, there is a landmark. So for example, several countries away, there is Paris, and inside Paris there is the L'Arc de Triomphe, and around it there is a roundabout, and this can be seen as a vertex somewhere else in the graph. And if you are traveling from A all the way to the Arc de Triomphe, you choose a path that looks somewhat like this. So you do some local travel, then you get on a highway, and along the highway you then travel to another country, then you traverse to another highway, and eventually you will reach Paris. And when you are traveling from B to the Arc de Triomphe, you will do some local travel here, and maybe join the same highway, and then travel all the way to Paris. And when you are going from A to B, maybe there's a better option when you leave the highway already here and go to B. So if we look at these 3 options to travel, what we can observe is the triangle inequality. Very simple observation. If you are traveling from A to C, the distance from A to C is always less than or equal the distance from A to B plus the distance from B to C. Because you always have the option of traveling via B, actually visiting B along the way, but maybe there is also a better option. But this is always an option, so this inequality is always true. And it's of course symmetric, so all the cyclic rotations of the inequality are also true. And what this is telling us is if we have the point P here in Paris, then you can say that the distance A to B plus B to P is greater than or equal to the distance from A to P directly, and the distance from B to A plus the distance from A to P is greater than or equal to distance from B to P. Now, we will generally assume that on our graph, this and this is the same distance, so on directed graphs it doesn't have to be the case, but yeah, most of our road networks is undirected anyways, and the simplification is usually close enough. And now, for this distance between A and B, what we have are two upper bounds. So the distance between A and B is greater than or equal to the maximum of two things. One of them is we get it from this one. So this is AP minus BP, and the other we get from this one. This is BP minus AP. So in other words, one of these is, yeah, these are the exact opposite numbers. So one of them is minus x, the other is plus x. And we know that the absolute value of this difference is a lower bound for the distance AB. And now it depends on the location of the landmark whether or not this is a useful lower bound. This is always a valid lower bound, but sometimes it can be the case that I want to go from here to there, and the point P is here, and what I get is that this distance is 16 hours, this distance is also 16 hours, so the lower bound I get is that this distance is at least 0 hours, and not useful at all, and this can be 7 hours. So this is a very loose lower bound that is not helping at all. But if the situation is like this, so that this is maybe 16 hours, 13 hours, and almost 3 hours, then we will get, or 3¼ hours or something, we will get an actual useful lower bound. And if you remember or learn about the A-star algorithm, the closer you can get with an actual lower bound to the actual value of a distance, the better you have an estimate. So if you now, how can you use this kind of estimate in your A-star algorithm? You can choose the specific landmark, in this case the Arc de Triomphe with Paris, and you can pre-compute the distances between this landmark and everything else in your road network. This is something you can do statically. You take the entire graph, you run the Dijkstra from this particular point in the graph, and then you compute all of these distances. And now, if a user comes with a query, and user says that this is the map of Europe, and I want to get from A to B, then you can run a star on this map. You will start exploring from A and trying to get to B. And as your lower bound, you now don't have to use just like as the crow flies. So yeah, if you think about running a star on actual road networks, the lower bounds you get by default are very, very bad. Because what can you get as a lower bound? So suppose I'm somewhere around here on the boundary of the space I've already explored, and I'm asking the question, what is the lower bound? How long it will take me from here to B? And like the only thing we can do reasonably quickly is say, like, if there was a direct highway from here to there, and you could drive along this highway at the top speed that is currently allowed in this country, so maybe 110 or 130 kilometers per hour, then you could divide the length by the speed and you will get the minimum time. And this time estimate is almost always very, very loose. So the actual travel time will be several times bigger because there is no direct highway. There are highways that are going in some other directions and you are not on them. So you have to reach them, you have to leave them, and so on. You get to do some local travel before you reach B. So the actual travel time will be maybe 3 times bigger than what you get from this optimistic lower bound. And this is where the landmark heuristic comes to play because with the Dijkstra from the Arc de Triomphe, we have computed actual travel times, of course, along actual roads. And sometimes the landmark, as I was showing here, was useless. But sometimes, if it happens to be roughly in the direction in which we are traveling, then the best is to imagine the actual triangle. So you are trying to estimate the distance from here to the goal, and you know the exact distance from here to there, and you know the exact distance from here to there. You can subtract those two, and you get a very good estimate of this particular distance. So the landmark heuristic, as long as your landmark is somewhere in the correct direction, is giving you a very good estimate of the actual travel time. And with these very good estimates, the A-star will very quickly only expand the nodes along the correct way, and it will reach the destination. Now, how can you make sure that this happens? Well, you don't have to use just a single landmark. You can take the entire map of Europe. You can choose maybe 15 of them that are somewhere strategically placed around the boundary. And for each of those points, you do the entire pre-computation. And now, whenever you are evaluating this, each of the landmarks itself is giving you a valid lower bound. All of those lower bounds are true, so you can just take the maximum of those. And if you chose the landmarks cleverly, then almost for any direction of travel within Europe, there will be at least one of the landmarks that is roughly in the correct direction or opposite direction, and therefore applies to give you the estimate of the travel time reasonably well. So already with this landmark heuristic, you should get something that will run reasonably well on your local machine. But there is also a second step, completely independent from the first one. This is, I will show this separately now. So, before we discuss this second optimization, we need to understand what the A-star algorithm actually explores. So, here is the starting node, here is the end we are trying to reach. And if magically we get a heuristic function that is exactly telling us the shortest distance from each node to the end, then what will A-star do is it will start by expanding the starting node and looking at its neighbors. And now the neighbor that is on the actual shortest path would be the one where the sum of the distance to it plus the estimate of the distance to the goal, because we are saying we have exact estimates. So it will be on the top of the priority queue. It will get expanded first, and then we will be expanding just the nodes along the shortest path, and only their neighbors will be even processed and inserted into the queue. So this is the ideal case that can happen. And now the looser our actual heuristic function is, the more there is a gap between the actual distance and the lower bound we are able to guarantee, the more we also have to explore around these vertices, so the more and more blobby the explored space is becoming. And by getting a good heuristic like the landmark one, we are reducing the size of this blob, but it is still a blob, so everything along the way will be explored. And this is, in some sense, dumb, because this is something a human would probably never do if they were doing this computation. So imagine that you have a long segment of a highway, and your solution is actually using this entire highway because it's traveling from a point that is somewhere over there to a point that is somewhere over here. But in your graph representation, the highway has exits, so there are nodes along the highway. At each of the nodes, there are some roads that are leaving the highway, so you can exit it, you can enter it, and there is some local neighborhood, some villages, and so on around each of the exits. And as the A-star algorithm progresses and the blob is expanding, then we will try to expand all of these vertices and also then go from them and try to explore all of these neighborhoods within the blob. And this makes no sense. So as a human, we know that if you already got on this highway, you will drive it all the way across, and those exits are completely meaningless. And those exits are completely meaningless, not just for us in this particular query, but for everybody who is traveling from far to the left to far to the right. Everything local here in these villages is only interesting to somebody who starts somewhere here or ends somewhere there. everybody else will just pass across and never visit them. So is there a simple way in which we can formalize this and teach an algorithm to do this as well? And the way how we can formally define something like this is as follows. So for each vertex of the graph, we can define a value that is called reach. And the definition is as follows. So we can imagine all of the possible shortest paths in the graph. Most of them do not pass through this particular vertex, but some of them do. And for each possible shortest path that passes through this vertex, we will take a look at the two segments, so from the start to this vertex, from this vertex to the end, and we will look at the length of the shorter one. So if there are many shortest paths that go through this vertex, for each of them, and this can be also like this, and this can be also like that as well, for each of them we will look at the shorter of the two segments, and out of those lengths, we will take the maximum. And what this is telling us is the following. So for example, if you have a node that has reached 17 minutes, this means that if you are traveling from point A that is more than 17 minutes from here, and you are traveling to point B that is also more than 17 minutes from here, then this node is definitely useless for you. And if you actually compute reach for each and every node that is just beyond the exit of a highway, and all of these nodes are nodes that there are some just villages, valleys here, then these nodes will all have very small reach, because all of the shortest paths that are actually passing through this node are somebody leaving from this area and then using the highway to go somewhere there far away. So all of the nodes with a short reach are automatically useless to everybody who is traveling from afar to afar. And reach is again a static property of the node in the graph that can be pre-computed. So you can take the entire road network, pre-process it to compute the reach of each vertex, and once you know this information, then if you have an exit where you change to a different highway, the reach of this exit will be high, this will be a useful vertex, but many of the other vertices you can cut the A-star search directly as it tries to expand the vertex, because for this vertex you can look at the distance from the start, you know this exactly, and it is large. You can look at the lower bound of the distance from here to the goal, it is also large. You can look at the reach of this vertex, it is small, and as it is smaller than both of this exact distance and this lower bound, then we can know that this vertex for this particular search doesn't make any sense, and we don't even put it into the priority queue. And what this does is then, on the real-life networks, with these two types of heuristics, landmarks and reach, you can get very, very fast running times, and essentially the number of expanded nodes is very proportional to the actual number of nodes on the shortest path it computes. So this works very, very well in practice, as I was saying, on static maps. So as soon as your maps become dynamic and you have traffic info that is changing the lengths of your edges, this approach is no longer useful, because both of the tricks are relying on pre-computing something for your static map, and yeah, there's no easy way to generalize this. I have left out one crucial part.
Sorry,
Yes?
I didn't understand why it is easier to pre-compute the reach of each node than it is to compute the shortest paths. Like, you need like all the shortest paths to have the reach.
You don't need all pairs of shortest paths. This is exactly what I was trying to say now, that the crucial bit I left out is how to pre-compute the reach efficiently. First of all, you could do, as you are saying, actual all pairs shortest paths, but this is computationally very, very expensive. The level 1 thinking, what you can do is you can pre-compute reach for a single vertex by essentially running, so you can imagine running the Dijkstra of shortest paths just from this vertex. You will get a tree of shortest paths. And now you can think about what do the shortest paths from another vertex to another vertex that actually have to pass through this one, what do they look like, and how you can get them from processing this tree. And there are also, so this is like the baseline solution that you can get to pre-compute reach faster, so you can go from n cubed time that you would need for all pair shortest path to something roughly like n squared log n if you are doing one vertex at a time. So you do the shortest path from there, and then you use the information to process the tree and find the longest, shortest path that can pass through it along this tree. But you can do also all other kinds of prunings and algorithmic improvements, which I will not go now into, but it is possible to pre-compute the reach for entire Europe again on your normal computer if you are doing it with a smarter algorithm. Yeah, okay. So this was an excursion into ideas that are not that difficult algorithmically, but can have a very large practical impact. And yeah, we have only a few more minutes left, so I'm not going to talk about any more problems, but I will spend the last few minutes talking to you about, let's say, practice. Practice is a good topic. So, most of us like solving problems. Like, probably the fraction of you that are forced to be here under some threats is very small. Most of you are here because you like solving problems, and we like to do it also in our spare time and call it practice. And how should you do that? And one of the most important lessons for myself as a contestant when I was still like going through the steps of studying in high school and at the university and learning to be better at problem solving, one of the most important observations for me was that you need to solve hard problems in order to improve your problem solving ability. When we are practicing for programming competitions, the problem solving ability is definitely not the only thing we are practicing for. There is a lot of benefit, for example, to being able to implement stuff so that it works on the first try. There is a lot of value in being able to debug efficiently, and also to use tools like, for instance, Valgrind, if you have it available on a machine. There is a lot of value in being able to implement inefficient solutions quickly, because on IOI-style contests you can still get partial scores, and you can also use them to set up a local testing framework where you can generate test cases, run the brute force solution, run your solution that is getting the wrong answer, and find a test case where they differ to understand whether this is a bug in the implementation or a problem with your idea and so on. So there is a lot of different aspects to programming, but the most important one, the fun one, the one why we are doing it, is problem solving. And you will not learn to be better problem solver by staying in your comfort zone. If you are solving problems where you look at the problem and you generally know how to solve it, then you are practicing other things, but not problem solving as such. For practicing problem solving, you need to look at problems that are beyond the boundary of what you can comfortably solve. And this is a moment, this is a place where many prospective future contestants get stuck and often even give up on the area completely, because once you start trying to solve these hard problems, what will inevitably happen is you will fail. As soon as you push yourself beyond your comfort zone and start working on problems that you are not guaranteed to solve, the meaning of you are not guaranteed to solve them is you will not solve all of them. For some of them you are lacking the proper technique and you don't know it yet. For some of them you have seen the technique but you are not familiar with it yet. You don't know how to recognize the correct patterns in the problem to apply it. And for some of them, yeah, you will just run out of luck and fail to explore the branch that leads to the solution. And this all will happen, with a significant frequency. Of course, there has to be some room to autocorrect. You cannot push yourself directly onto the hardest problems,
and then solve nothing, and then learn nothing from it. You learn the most from problems that are just outside your comfort zone. So, for instance, if out of every 3 problems you attempt to solve 2 and you fail 1, and then you need to go and read the solution and maybe also try solving it afterwards to make sure you can implement it. This is still a very good ratio that is very close to being optimal in terms of your problem-solving ability being exercised. But at the same time, and this is what I was getting to when I was saying this is a place where many people quit, it's very, very hard on our psyche, because most of us, in most environments of our life, we are conditioned to think of mistakes, of failures as something bad. So if I'm not able to solve all of the practice problems, if I'm getting stuck on many of them, it's very easy to tell to ourselves that I'm a failure. I don't have what it takes to be a good competitor, and to give up, because we don't like the feelings associated with being a failure and being bad at something. And the mindset that will help you and turn you from a good competitor into a great one is to realize that I have to fight these feelings actively, and I don't have to accept them at face value and accept that when I fail, I'm doing something wrong. I have to realize consciously that when I sometimes fail and sometimes succeed, I'm doing things exactly right. And failure is part of the process of training and becoming better. So it's not bad if you fail, and it's not bad if you fail repeatedly. It's bad only if you give up afterwards. So yeah, this was when I came through the process of getting from personally dealing with the same feelings I'm describing, and thinking of myself as I'm a failure, I'm not good because I'm failing so much and there are so many problems that I was not able to solve. When I got through it and I realized that this is actually how it all works, and that a failure is a part of the learning process, then I think this helped me be better. And I think that talking about it to you now and helping you think about this on your own is giving you the tools to succeed as well. So I hope that this will help you in the future, and now you will be able to see yourselves in a different light when you fail to solve a problem. Failing to solve a problem is good. Failing to solve many problems and solving other problems in between is also good. It still means you are making progress, and actually for your problem solving ability, you are doing the best that you can. And that's it from me now. Thank you for your attention, and tomorrow we will have this last of this week. Okay, so just very quick instructions. Today you should have again a contest set up. It's again set up to be a team contest as just as yesterday, and probably today will be even somewhat more difficult on the top end, but we will see. Yesterday I was very pleased with the performance of the top teams. I mean, everything got solved and nobody solved everything, so this is the ideal state which each, for example, ICPC World Finals set is aiming for. For today's set, I'm aiming for, I'm not sure whether everything will get solved. We'll prove me wrong. Okay, so good luck in the afternoon.
Io credo che